Okay, so as I told your classmates here that won't have a whole lot to go over, but sometimes just doesn't work out that way. We'll do our best to try to keep it in that format. As we had mentioned, this will get a little tougher because it's going to be the reactions that will be a little more difficult. And when you look at symmetric reagent, that would be one of the reasons. And we'll talk about that here in just a few moments. So what I want you to be able to see, if I open up the window and not drop my scissors on anybody, that could be bad. So what maybe comes to mind when you see alkenes, and you probably really don't have an answer for that, and I wouldn't expect you to, but maybe. Anything? Okay, double bond, that's correct. And I'm looking at like your pens there, what the outside of your pen, not so much this, is it Stanley here? Plastics, that's right, because plastics are made of alkene compounds. It's just a repeating unit called a polymer, to where you have ethene, 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 and since ethene is a monomer, but when you hook them all together, then you call it a polymer then. So plastics is, again, made of that polymer called ethene, called polyethylene. Okay, now I could have swore I just saw my clicker not too long ago. Next to my computer. Oh no, that runs Wozniak there, or Wasowski or whatever his name is. Wasowski. I'll get it right one of these times. Okay. I don't have that much stuff on this desk. How can I not see this or find it? Oh, that's because it's over here. It was on this mug rug. Okay. So moving forward. Okay. Let's see here. I want to get through. I don't know how far down this sheet we need to get. And it's into 4-3. Okay. So a lot of this follows a similar pattern to that of the alkanes. Okay. Not only are they named similar, but some of their physical properties are identical as well, because as we look at this, okay, we know that methane, or natural gas, okay, and then is in a gaseous state. We know ethane is in a gaseous state. Propane, that you use to maybe do your grilling, is in a gaseous state. But then once you get to butane, okay, that might be something you use to light your charcoal grill, whether it's one that has an igniter that's just not working. You pull the trigger on this, and then from butane, the spark then creates a little flame, because butane is in a liquid form. So there's some similarities between alkanes and alkenes. Okay, this is just a basic formula, but if this was alkanes, you have to account for the hydrogens on the end. That's why that would have 2N and then plus 2 on there. And we'll illustrate that here in just a moment. Okay, this one, yes, okay. And we'll illustrate what we mean by not being able to dissolve in water, because again, it is, as you can see, nonpolar, which doesn't mean anything to you now, but we'll hear in just maybe a couple of moments. maybe there's nothing to write for that, because I want to do this one, right? And then I just want to do a couple things up on the board, and then that will be it for today. And I'm thinking that on Wednesday, that's why that was blank over on the board. It says isomerism of alkenes, and we'll dive maybe more into that on Wednesday. But we need to illustrate this here first, and then that'll make a little more sense. So again, this probably doesn't mean anything until we actually apply that. Okay, take it everyone has this content that wants it. Okay. Let's hit pause here for a moment. Okay, so one of the things that may come up in, not so much at this level, but the next one. Okay. If you feel, you don't need to write this down. It just explains that, what did it say about some of the physical properties? Are alkenes soluble in water? No, because they're nonpolar. Because with water, okay, and this goes back to this compound, of course. And if you write it down, fine. If not, it's not that big of a deal, okay? Because if you know it, if you understand it today, you're going to know it the next time you see it. You're going to know it the next time you see it. What happens is, typically when we do dot diagrams, we usually just leave them in a plane of 180 degrees. Now, there's some that are a little more complex than that. There might be trigonal planar like that of methane, but with water, it's not technically 180 degrees because what we see happening here, okay, and I'm just going to put that X down here, is that, oh, I didn't quite do that right. Well, it's right, but it's not how I want it to look. I'm going to end up using my hand here pretty soon. Oh, that's because I don't have any. I washed them all, except this one. Okay, I want this one a little more to the side. Okay. Because notice that when you look at things, let's say you have a glass of water and you put something in that water. It could be this marker, and it's sitting like this. You don't see the marker going straight down like this, do you? And for the same reason, what happens if you have a drizzle or rainfall and then the sun comes out and it's still raining? Yeah, you see a rainbow. You're looking at your lab partner and what?
There was one this morning.
Oh, okay. Well, you're pointing at your lab partner. I was gonna maybe she's the rainbow. I don't know. Isn't it like a pot of gold right next to you or not?
No.
Well, it's supposed to make you feel better. I don't know if it's working or not. Not that, because I just thought, well, maybe you're the rainbow.
Yeah,
Maybe. Okay. But that means that water it's not that it bends materials, it's because it's a bent molecule. So what happens is, as you could say, light comes in, and then that's why we wanted these hydrogens out a little further, because this is partially negative, okay? And then these how did I do that? These hydrogen atoms then are what we call partially positive then, okay? Oops, that's supposed to be a plus sign, not another hydrogen. Okay? It looks like an 8. I'll make it a little bigger. It looks like that. That means partial. Okay? And therefore, does water, for instance, conduct electricity? Yes, it does. It's because of this charge on these compounds, really, you could look at, okay? And when we look at something like this, okay, so we'll just keep it really simple. And here, there's really, these electrons are being shared equally. And then, okay, there's no really bouncing back and forth with these electrons. They're just sharing them. This oxygen or these hydrogens, these electrons stay out just a little further because it's just what we call a partial charge. Okay, that's why even the bigger compounds that you put here, even as big as octane, crude oil, anything to that nature, they're all nonpolar bonded. So does oil mix with water? No. And this is why. It's because these are nonpolar, and that is a polar compound. Okay? So the last thing that we want to go over then for today is we talk about butene. Or let's start with butane instead. Okay? So if we have this from last chapter, does that have any isomers to it? Yes. What would an isomer of that possibly be? 2-methylpropane. Okay? So we're going to look at these side by side then. Okay? Then we're going to put, how would we write butene then? And we're basing this off of some prior knowledge you might have, because it's one of the first things that you had said. It's a double bond. So we'll go ahead and put that double bond here. Then we'll put all of our single bonds in here. Okay? That has an isomer. What would be the simplest thing that you could do to create an isomer for this? Yeah, just move it over one. Okay, so with butane, we only had one isomer. Here we've got butene. Are we done with isomers? No, we're not, because we've done one of them now. And I want to say it was one of the last things you wrote down, or maybe it was one of the last things that was actually on your handout. I think it says butene exists as 2 isomers. It doesn't tell you how, though. Okay? But what could we do with that? Notice inside that box you don't have methane. You have a what group? You have a methyl group. Okay? So what that would probably mean is just like what you did here. You took this off of the end and then just moved him here to the middle. So with everything we know, could we do the same thing here? Sure. We can take that off that box. Or take it off the box. It's already in the box. We could take that off of the end. Okay. So once we take that off, those are still there. This. Then we just have to do one more thing. We need to replace that. Now, you're right. I didn't quite get this down in time because this is what I wanted to do. Well, we must have to put that here. And why would that be wrong, do you think? Yeah, this is still butene. If you really want to be specific, you could say 1 butene here. That's 2 butene. And then this will still be 1 butene. It's just more so of a bent structure. So we don't put it on this carbon. Rather, we put it on this one. Okay, so that's what happens with the isomerism between alkanes and alkenes, is that there's more that exist in this organic family just because that double bond can move from one side to the other. Of course, the longer of a chain that you get, well then the amount of isomers that you get is really going to increase. And one of the things that was on your exam, the isomers for, what was it, hexane, which I think there's actually 4 of those, which isn't bad. You get up to maybe heptane, and there's maybe, I don't know, 8, 9, and then of course, the longer the parent chain you get, the more isomers exist. Okay, so we can pick up with this on Wednesday. We'll be in the lab tomorrow making your slime. All right, we'll catch up to you next time.